Hi, I'm Jeff Groh, and this is Calculus 2, Final Exam Review. We're going to begin with a bunch of integrals. The integral of x squared plus 3x minus 5 dx. I should make this plus 2 points if you get it right, minus 1,000,000 points if you get it wrong. This is so easy. If you can't do this, you ought to fail the course. We use the power rule for antiderivatives. And don't forget plus c. Next, a basic definite integral. This is a basic test of your understanding of the fundamental theorem of calculus. First, find an antiderivative, evaluate at the endpoints, and subtract. Negative 2/3. Then, a basic u sub. U is x squared plus 1. Du is 2x dx. Divide the 2 off. We transform this integral as 1/2 the integral of u to the 1/2 du. We have 1/2 u to the 3/2 times 2/3 plus c. And so we get 1/3 times the quantity plus 1 to the 3/2 plus c. On the next problem, we're integrating x e to the x squared dx. What is the method of integration? Remember our paradigm of 4, u sub, partial fractions, trig sub, and integration by parts. While this might look like an integration by parts problem, it's not. We see the derivative of something lying around. So this is a u sub problem. U is the thing that has its derivative, more or less, lying around. So du is 2x dx. We'll divide the 2 off and transform the integral as 1/2 the integral of e to the u du. That's 1/2 e to the u plus c, and so our answer is 1/2 e to the x squared plus c. The very next problem is the integral of x e to the x dx, and this is clearly an integration by parts problem. Let's use the tabular method. We'll set u equal to x and calculate derivatives down the first column, down to 0. That's where you stop. We'll put e to the x in the second column and we'll integrate down the second column. We multiply down diagonals and alternate signs. So the answer is x e to the x minus e to the x plus c. On the next problem, we have the integral of the natural log of x dx. Name the method. On a problem where you see something that you'd rather differentiate than integrate, when you see a problem where the integrand is something you'd rather differentiate than integrate, it's an integration by parts problem in all likelihood. Let's do this one the old-fashioned way. We'll set u equal to the natural log of x and dv equal to everything else, including the differential. Du then will be 1 over x dx, and v will be x. The integral is transformed into x log x minus the integral of x times 1 over x dx. The x's cancel. The answer is x natural log of x minus x plus c. On the next problem, we're given the integral of the square root of 1 minus x squared dx. Now, Don't misidentify this as one of the important integrals I asked you to memorize. I did ask you to memorize the integral of 1 over the square root of 1 minus x squared, and that's simply arcsine x plus c. However, this isn't that. On this problem, we have a difference of squares under a radical. That's definitely a trig sum. And because it's in the form 1 minus x squared, we choose x equals sine theta as our substitution, because 1 minus sine squared is cosine squared, and the square root of cosine squared will then end up being cosine. We convert a difference of squares into a perfect square using Pythagorean identities. Dx then is cosine theta d theta. We have the integral of the square root of 1 minus sine squared theta times cosine theta d theta. And that simplifies into the integral of cosine squared theta. It is at this point that you need to use the half angle identity. Cosine squared theta is 1/2 times the quantity 1 plus cosine 2 theta. I may as well write down the other ones so you can remember them together. Sine squared theta is 1/2 1 minus cosine 2 theta. So here we have 1/2 the integral of 1 plus cosine of 2 theta. That's 1/2 times the integral of theta, that's 1/2 times theta plus 1/2 sine of 2 theta plus a constant of integration. At this point, we need to use a double angle identity. Sine 2 theta is 2 sine theta cosine theta plus c. From here, we have to go back to the original substitution and create a right triangle. If sine is x, we'll express that as a fraction, x divided by 1. Sine is opposite over hypotenuse, and so the adjacent side will be the square root of 1 minus x squared. This had better show up again, or else you screwed up. It follows then that our answer is 1/2 times, solving for theta, theta is going to be the arcsine of x, sine theta is just x, cosine theta is adjacent over hypotenuse. That's the square root of 1 minus x squared times x, and then plus c. On the next problem, we're integrating 1 over x times 1 plus x dx. What is the method? We have 4 methods: substitution, trigonometric substitution, integration by parts, and partial fractions. Partial fractions applies when you have an integrand that is a rational function. What is a rational function? A rational function is a function that talks and makes sense, right? No, a rational function is a ratio of 2 polynomials. A polynomial divided by a polynomial, and that's exactly what we have here. Technically speaking, the method of partial fractions is not really an integration technique so much as it is an algebraic technique designed to take rational functions and split them into terms that are simpler to integrate. So, we'll split this up into 2 pieces, a over x and b over x plus 1. Multiplying both sides by the denominator on the left-hand side, we get 1 is a times x plus 1 plus b times x. Make sure you understand that step. Next, we'll let x be 0. If x is 0, then we end up with a equals 1. The next obvious choice for x is to let x be negative 1. If that's true, we get b equals negative 1. The integral then is 1 over x minus 1 over x plus 1. We have then the natural log of the absolute value of x minus the natural log of the absolute value of x plus 1 plus c. On the next problem, we're integrating from negative 2 to 2 x times the square root of 1 plus x squared dx. It should be obvious that the integrand is odd, and so the answer is 0. But just in case you didn't understand that argument, let's suppose that I set f of x equals x times the square root of 1 plus x squared. I claim that f is odd. What does that mean? Is a function odd when it does inappropriate things in social settings? No. A function is odd if f of negative x is negative f of x. If that should happen, then the graph must do the opposite at negative x compared to what it does at x. Whatever happens at negative x is going to be the negative of what happens at x. Is this integrand odd? Well, if you replace x by negative x, sure, you'll get a negative x out front, and then 1 plus negative x squared. The negative on the x under the radical gets squared away, whereas the negative out front can just be detached as an independent negative. We end up with the negative of the original function. Therefore, f is, in fact, odd. And so whenever you integrate a function that is odd from negative a to a, you must get 0. On that last problem, I want you to be able to identify that the integrand is odd by inspection. And since the limits of integration went from negative 2 to 2, the answer is 0. Just write equals 0. No further work is really required. You might comment, integrand is odd. On the next problem, we're integrating the square root of 1 minus x squared from negative 1 to 1. I want you to be able to recognize that the integrand is a circle. Not the whole circle, just a semicircle, the upper half, since we're dealing with the principal square root. The principal square root always outputs non-negative values. Whenever you see the radical symbol, that's not referring to any old square root. That's referring to the principal square root, and that's the non-negative one. If you square both sides here, you'll get y squared equals 1 minus x squared, and hence x squared plus y squared equals 1. It should be obvious now that you're dealing with a circle of radius 1, but with the principal square root, you only get the top half, right here. What you should recognize is that you're getting 1/2 the area of the disk of radius 1. And so the answer is pi over 2. On the next problem, we are integrating from 0 to 2 pi sine x dx. You should immediately state that the answer is 0 because you're integrating the sine function over an entire period. Next up is the integral from 0 to pi of sine x dx. You should immediately state that the answer is 2 because you're integrating one bump, and everyone knows one bump gives you 2. On the very next problem, you're integrating sine x from 0 to pi over 2. you should immediately write 1, because everyone knows that half a bump gives you 1. On the next 3 problems, we're asked to determine whether the following integrals converge or diverge, and to justify our answers. The first one is the integral from 0 to infinity of 1 over x squared plus 1 dx. This is an improper integral because one of the limits of integration is infinity. So we should rewrite this as the limit as L goes to infinity, the integral from 0 to L, 1 over x squared plus 1 dx. You should recognize this integrand. This is the one I asked you to remember. And so we get the limit as L goes to infinity, the inverse tangent of x evaluated from 0 to L. Plugging in L, we get the limit as L goes to infinity, inverse tangent of L minus the inverse tangent of 0, but the inverse tangent of 0 is 0. The graph of inverse tangent looks like a sideways tangent curve. As you send L to infinity, the value of the function tends towards pi over 2. So our answer is pi over 2 and converges. The statement of the problem specifically asked you to determine whether or not the integral converges or diverges. Since we have a finite limit, the integral converges. The next problem, we integrate from 0 to 1, 1 over the square root of x dx. This is improper because the integrand is not continuous at 0. It follows that we need to write the limit as L goes to 0 from the right, the integral from L to 1, 1 over root x dx, and we might replace that integrand by x to the minus 1/2. We have to go to 0 from the right because we have to back off from the problem and then go back towards it. We get the limit as L goes to 0 from the right of x to the positive 1/2. When you divide by 1/2, it's the same as multiplying by 2. Evaluated from L to 1. This gives us the limit as L goes to 0 from the right, 2 times the square root of 1 minus 2 times the square root of L. Since L is going to 0, the second term vanishes and the limit is 2. Therefore, the integral converges. The third problem in this series is the integral from 1 to infinity of 1 over the square root of x dx. Again, this is improper because one limit of integration is infinity. And so we'll write this as the limit as L goes to infinity, the integral from 1 to L, of x to the negative 1/2 dx. This is, of course, the limit as L goes to infinity of x to the positive 1/2 times 2, evaluated from 1 to L. Evaluating, we have the limit as L goes to infinity, 2 times the square root of L, minus 2. As L goes to infinity, the integral goes to plus infinity, and therefore it diverges to plus infinity. On the very next problem, we're given 2x plus 1 over x plus 1 quantity squared times x squared plus 1, and asked to find the partial fraction decomposition of this rational function. It has a couple things that we didn't have in the earlier problem, but we do not want to integrate this. We just want to find the partial fraction decomposition. So we're first going to rewrite this as a over x plus 1 plus b over x plus 1 squared. You have to start at 1 and go to whatever power appears here. The next factor in the denominator is an irreducible quadratic. For all irreducible quadratics, you need a linear numerator over that quadratic. Clearing the denominators on both sides by multiplying by the denominator on the left-hand side, we obtain 2x plus 1 is a times x squared plus 1 plus b times x squared plus 1 plus the quantity cx plus d, don't leave the parentheses off here, times x plus 1 quantity squared. Now, it is possible to choose some strategic values of x to eliminate some terms. If we choose, for instance, x equals -1, the left-hand side becomes -1. On the right-hand side, the first term drops, the last term drops. If x is -1, we end up with 2b, so that b is -1/2. I'll put that in a little bucket there. There are not very many other nice choices other than x equals 0 as a possibility. If x is 0, 1 is a plus b, which is -1/2. The x is equal to 0, so the c term drops. We end up with plus d. Moving 1/2 to the other side, we get the equation a plus d equals 3/2. We need two other equations, though. So let's let x equal 1. If x is equal to 1, then 3 is equal to, we have 2 times 2 is 4a. We'll have 2b, but b is -1/2. We'll have c plus d times 4. That's 4c plus 4d. If we move this -1 to the other side, we end up with 4 equals 4a plus 4c plus 4d. We can divide the 4's off, yielding a 1 on the left-hand side. And that yields the equation a plus c plus d equals 1. Note that from the last two equations, if a plus d is 3/2, then we get 3/2 plus c equals 1, which means c is -1/2. So we have b, we have c. We need one more equation. We have one more choice that we may make. Let x be 2, why not? Then 5 equals, we'll have 3 times 5. 2 squared is 4, plus 1 is 5. 5 times 3 is 15. We'll have 5b, and we know that b is -1/2. C is -1/2, but we're choosing x equals 2 plus d times 2 plus 1 is 3, squared is 9. We have then that if we move this 5/2 over to the left, this is 10/2. We'll combine that with another 5/2. we'll end up with 15 halves equals 15a. We'll have another minus 1 times 9. That's minus 9 plus 9d. We'll move the 9 over, which is 18 halves. That makes 20 and 13, that's 33 halves. So we have a couple equations. 15a plus 9d equals 33 halves, and we have a plus d equals 3 halves. Let's multiply this through by 9. 9a plus 9d equals 27 halves. If we subtract these equations, we'll get 6a is equal to 6 halves. In other words, a is 1 half. If a is 1 half, then d has to be 1. Our answer is finally 1 half over x plus 1 minus 1 half over x plus 1 quantity squared plus, left parenthesis, negative 1 half x plus 1 over the quantity x squared plus 1. There is another way to have done that last problem, and it's okay if you use an alternative method. On the next problem, we are asked to use Simpsons rule with n equals 4 to approximate the integral from 0 to 1 of the square root of 1 minus x squared dx. The formula starts with delta x. Delta x is b minus a over n. In this case, that's 1 minus 0 over 4, since we're told to use n equals 4. After calculating delta x, you should calculate the elements of the partition. x0 is the left-hand endpoint. x1 is 1/4. x2 is 2/4, or 1/2. x3 will be 3/4, and x4 will be the right-hand endpoint 1. The formula is like this. The integral from a to b of f of x dx is approximately, at least when n equals 4, delta x over 3 times f of x0 plus 4 f of x1 plus 2 f of x2 plus 4 f of x3 plus f of x4. It follows that in this case, if our integral is I is approximately 1/4 over 3, the square root of 1, plus 4 times the square root of 1 minus 1/4 squared, plus twice the square root of 1 minus 1/2 squared, plus 4 times the square root of 1 minus 3/4 squared, plus the square root of 1 minus 1 squared, which is 0. Our next problem says, find the volume of the solid of revolution generated by revolving the region bounded by x equals 1, x equals 2, y equals 0, and f of x equals x about the x-axis. So y equals 0 and y equals x are like this from 1 to 2. So the region that's bounded is shaded here. We're revolving this about the x-axis. We expect to get a region that is called a frustum of a cone that has had its tip chopped off. We're going to use the method of disks. The method of disks says the volume is pi times the integral from a to b of the function squared. For us, that's pi times the integral from 1 to 2 of our function x squared. Using the fundamental theorem of calculus, that's pi x cubed over 3 evaluated from 1 to 2. Leaving the pi over 3 out of this, that's going to be pi over 3 times 8 minus 1, or 7 pi over 3. Next, we determine convergence and or divergence of infinite series. I want you to do 3 things on these for the most part. 1, state the test you're using. 2, show me that you're using the test and implementing it. And 3rd, state your conclusion. On the first one, it's the sum as n goes from 1 to infinity of 1 over n. And this one, you don't need to do all 3 steps because it is obvious that this is the harmonic series. And everyone knows the harmonic series diverges. The next one is, you guessed it, the alternating harmonic series, and everyone knows that it converges conditionally. Next, we have the sum as n goes from 1 to infinity, 1 plus 1 over n to the power n. You should suspect that the terms don't go to 0. In fact, you might even know that the limit as n goes to infinity of 1 plus 1 over n to the n is equal to e. If you don't remember this, you should be able to calculate that by taking the limit as n goes to infinity of e to the natural log of 1 plus 1 over n to the n. By properties of logs, you can bring this n out front and then flip that n down into the denominator. Now you have a L'Hopital's rule case. That gives you the limit as n goes to infinity of e to the 1 over 1 plus 1 over n times the derivative of the inside, which is negative 1 over n squared, divided by the derivative of the denominator, which is negative 1 over n squared. Since the terms have a limit that is not 0, this series diverges by the divergence test. On the next series, we have the sum as n goes from 1 to infinity of n factorial over e to the n. We know that factorial growth is greater than exponential growth, so you suspect that this series diverges. But we need to apply a test. Since we have a factorial, this is definitely a ratio test problem. We'll take the limit as n goes to infinity. The absolute value doesn't matter. N plus 1 factorial over e to the n plus 1 times e to the n over n factorial. The factorials cancel except for this factor n plus 1. E to the n cancels, and the limit is plus infinity. That's greater than 1, and therefore the series diverges. The last problem in this series is the sum as n goes from 1 to infinity of 1 over 2 to the n. Yes, you may use the root test, but this is a geometric series. So we can use the geometric series test. The common ratio is 1/2, which has a magnitude less than 1, and therefore the series converges. On the next 2 problems, we are to find the interval of convergence of a power series. we start with the sum as n goes from 1 to infinity of x to the n divided by n. In this case, the coefficients are 1 over n, and the center is 0 because we're untranslated. The radius of convergence is the limit as n goes to infinity. The formula is an over an plus 1, kind of an upside down ratio test, because we had to divide the ratio test coefficients over. This gives us the limit as n goes to infinity of 1 over n divided by 1 over n plus 1. Well, that limit is 1. It follows then that the interval of convergence contains everything from -1 to 1. The only question is, what happens at the endpoints? At x equals 1, we have the sum as n goes from 1 to infinity of 1 over n. That's harmonic, and that diverges. At x equals -1, we get the sum as n goes from 1 to infinity of -1 to the n over n. That's alternating harmonic, which converges. It follows then that the interval of convergence is the half-open, half-closed interval from -1 to 1, including -1, not including 1. On the next problem, we have the sum as n goes from 1 to infinity of x minus 2 to the n divided by 4 to the power of n. In this case, the center is 2, and the coefficients are 1 over 4 to the n. The radius of convergence is the limit as n goes to infinity of 1 over 4 to the n over 1 over 4 to the n plus 1. You can see that we're going to end up with 4. The interval of convergence is then everything from 2 minus 4, that's -2, to 2 plus 4, which is 6, or at least it contains that. We still need to check the endpoints. At x equals 6, we have the sum as n goes from 1 to infinity. 6 minus 2 is 4. We have 4 to the n divided by 4 to the n, which is 1. This diverges by the divergence test. At x equals -2, we'll have the sum as n goes from 1 to infinity. We'll have -4 to the n divided by 4 to the n, which is just -1 to the n, which again diverges by the divergence test. It follows then that the interval of convergence is the open interval from -2 to 6. On the next problem, we are to find the first 4 terms in the Taylor expansion of f of x equals the square root of x expanded around the center c equals 1. The way to proceed is to calculate derivatives. The first derivative is 1/2 x to the minus 1/2. The second derivative, we bring the negative 1/2 down, we'll have -1/4 x to the minus 3/2. And then for the third derivative, we'll have positive 3/8 x to the minus 5/2. We need to evaluate each of these at 1. So f of 1 is 1. F prime of 1 is 1/2. F double prime at 1 is -1/4. And F triple prime at 1 is 3/8. We then write down the first 4 terms. The formula is f of x naught plus f prime at x naught, x minus x naught, plus f double prime at x naught divided by 2 factorial x minus x naught squared, and so on. So in this case, we'll have 1 plus 1/2 x minus 1 minus 1/4 over 2 factorial x minus 1 squared plus 3/8 over 3 factorial x minus 1 cubed. And those are the first 4 terms. On the next problem, we are to calculate the area of the inner loop of r equals the square root of 2 minus 2 cosine theta. Let's graph first of all, the theta r graph. The square root of 2 is about 1.414. If we have an amplitude of 2, the minimum line is going to be below the x-axis. We have an upside down cosine curve, so we start at the lower limit and then go up like this, completing the cycle in 2 pi units. It follows then that the polar graph starts with a negative radius, goes through the origin somewhere between 0 and pi over 2, reaching a positive radius of square root of 2 at pi over 2. We get a maximum radius at pi, and then back down after that. We need the area of the inner loop, so we need to find the angles at which the curve crosses the origin. So we'll set 0 equal to r and solve for theta. We'll have cosine theta is the square root of 2 over 2. That gives us pi over 4 as one of our angles. Don't choose 7 pi over 4 for the other angle, because if you do, you'll be integrating from pi over 4 to 7 pi over 4, which gives you the wrong area. Rather, negative pi over 4 would be a better choice. But even better yet, integrate from 0 to pi over 4 and then double it. The formula for the area is 1/2 the integral from theta naught to theta final, r squared d theta. So for us, we'll have double that 1/2 integral from 0 to pi over 4, root 2 minus 2 cosine theta quantity squared d theta. We have then the integral from 0 to pi over 4 of 2 minus 4 root 2 cosine theta plus 4 cosine squared theta d theta. At this point, you need to use a half angle identity. Cosine squared theta is 1/2 times the quantity 1 plus cosine 2 theta. So if we replace cosine squared with 1/2 1 plus cosine of 2 theta, the 2 will cancel with the 4, leaving a factor of 2. We'll get the integral from 0 to pi over 4. When we distribute this 2, we'll have a 2 plus 2 is 4 minus 4 root 2 cosine theta plus 2 cosine of 2 theta d theta. Calculating the antiderivative, applying the fundamental theorem of calculus, we have 4 theta minus 4 root 2 sine theta. When we integrate cosine 2 theta, we get a 1/2, which will cancel the 2. We'll have sine of 2 theta evaluated from 0 to pi over 4. When we plug in pi over 4, we'll have pi. The sine of pi over 4 is root 2 over 2. 2 times pi over 4 is pi over 2. The sine of pi over 2 is 1. We'll subtract what we get when we plug in 0, which is 0 across the board. Root 2 times root 2 is 2. That's going to cancel the 2 down here. We end up with pi minus 3. We come to the final problem on the practice exam, and that is to find the surface area of the surface obtained by revolving the curve r equals 2 minus 2 cosine theta about the x-axis. It's pretty easy to see that this curve is a cardioid. I'll let you figure out the rest of this graph. Go ahead and try that. When we revolve the cardioid about the x-axis, we really only need to revolve the top part, where theta goes from 0 to pi, because we'll sweep out the entire surface with just that little hook. The formula for surface area is the integral from theta naught to theta final. The idea being, for surface areas, you take little elements of arc length, ds, and multiply it by the distance around, which is determined by a circle of radius y. Y is r of theta times sine theta. So this is the circumference around times the element of arc length, which in polar coordinates is r prime squared plus r squared under a radical. We have then the surface is the integral from 0 to pi, 2 pi, 2 minus 2 cosine times sine, square root of the derivative of 2 minus 2 cosine is 2 sine squared plus 2 minus 2 cosine squared d theta. Let's factor as much as we can before we try to integrate. This 2 can come out and make a 4. We'll have 4 pi, the integral from 0 to pi, of 1 minus cosine times sine, square root 4 sine squared plus 4 minus 8 cosine plus 4 cosine squared d theta. 4 sine squared plus 4 sine squared is 4. We'll combine that with the other 4 to make an 8, and we'll bring the 8 out of the square root. 8 comes out of the square root as a 2 root 2, leaving just a 1 minus cosine. We'll have 8 root 2 pi, integral from 0 to pi. We'll have 1 minus cosine, sine, square root 1 minus cosine. 1 minus cosine times the square root of 1 minus cosine is 1 minus cosine to the 3/2. We can then do a u substitution. If we set u equal to 1 minus cosine theta, then du is sine theta d theta, because the derivative of cosine is negative sine. We have 8 root 2 pi, the integral. If theta is 0, then u will be 0. Cosine of 0 is 1. 1 minus 1 is 0. If theta is pi, cosine of pi is negative 1. We get 1 minus negative 1. That's 2. We'll have u to the power of 3/2, and then sine d theta is du. Integrating, we have 8 root 2 pi, u to the 5/2, divided by 5/2 is multiplied by 2/5, evaluated from 0 to 2. keeping in mind that a to the 5 halves is a to the 2 plus a half, and that's a squared root a. So 8 times 2 is 16, root 2 pi over 5, times 4 root 2 minus 0. 4 times 16 is 64. Root 2 times root 2 is 2. So we get 128 pi over 5. And that finishes the review.